Well, first of all, thanks for sticking around, and also to keep a little tradition going of lunar balls. I've done this so much, I've run out. We just ordered a whole bunch more. I don't know what to do. Okay, are you awake? For several years I've been, too many years probably, but I've been trying to produce a synthesis of all the data I can round up on Apollo 17's visit to Taurus-Littrow on the moon, of course. And this is Taurus-Littrow, and you see all the various craters that are important to that synthesis, as well as a number of other features that some actually have been alluded to and will be alluded to at this conference. Next, please. Probably the most important data set that I had to work with was Dick Morris's Is-FeO maturity data from the deep drill core at Apollo 17. It's the best, essentially a complete drill core. Might have compacted a little bit at the top, as all the cores do, but nevertheless you can see there's a lot of variability in the Is-FeO. And Dick was kind enough to send me 2 or 3 years ago the half centimeter by half centimeter data that he used and summarizes in this particular figure. And I then logged that, 3 meters of half centimeter data. And it supports the definition of a number of regolith ejected zones. The fortunate geological aspect of Taurus-Littrow is that there are several geological units that, when sampled by cratering and with ejected, you can actually identify the source craters of the ejecta zones, regolith ejecta zones in this core. And I hope you believe that, because everything sort of depends on it. But the geology is quite specific in the various units that have been affected. Next. And one of the things that very early on started to puzzle me, and then I think is very clear, particularly when I ran across a paper by Bauer on halos around zircons. Those of you who have had petrography in education situations know about pleochloric halos in biotites. Well, he finally had the instrumentation to look very, very close at these, and guess what he found? Nanophase iron in these halos. And that started to make some sense relative to the importance of alpha particle radiation internally within the regolith and within regolith particles. And that's what this one little graph shows you, is that there's a very strong dependence on the current values of thorium and uranium with the delta Is-FeO. Now, what is delta Is-FeO? That comes from that logging of the drill core. And those zones are indicated there. It turns out that in this drill core, when you start to look very carefully at it at the half centimeter level, you see a slight rise for a centimeter or so, a few centimeters, and then a sudden drop, and then a slight rise and a sudden drop. And I puzzled over that for quite a while until I started really to look at what was going on at Shorty Crater, but that's another story. And what those drops are resets, micrometeorite resets of the IS component of Is-FeO. But it doesn't affect your ability then to sum the rises, the slow rises that before the next drop. And when you sum those, that gives you this delta Is-FeO. That is the exposure of the particular zone with time. Now, I immediately started to think, well, can I turn that into an age? Can I turn that delta Is-FeO into an actual exposure age? Because clearly each ejection zone came in with some remnant exposure age related to the pre-source crater regolith that existed at the time of the impact. And next, please. Well, fortunately, we had a very nice station 6 that involved the boulder. This particular diagram is from Wolf and his very fine geological paper on samples and other aspects of the Taurus-Littoral area. That boulder left a nice track, and that's very important. And it turns out in the study, probably won't go into this further, but as these boulders run down, this was 1.5 kilometers, and they don't really roll, they bounce. They leave a crater chain behind them, which we call tracks. But in that process, they're shedding their exterior material quite a bit. And these boulders particularly are very rich in uranium and thorium, comparatively to most of the regolith and other rocks, certainly in the basalts. And so they give you contrast because of that shedding. And when this boulder finally came to rest, next please. Next please. There we go. When it finally came to rest, it shedded some more, and I've outlined in some dotted area there the splatter from the final impact of that boulder. And what that two consequences of that impact is that the splatter covered the regolith in place on the mountain and on the slope, and also actually coming on top of that splatter was two of the boulder fragments that created a continuous shadow. There's been some very fine, next please, there's some very fine cosmic ray exposure age work been done on this boulder, and when you average the three analyses that were published back in the 70s, you get an exposure age for that impact, for that arrival of the boulder of about 19.5 million years, plus or minus about 1.5. But we'll use 19.5 as the exposure age. Next, please, there you go. The continuous shadow was underneath fragment number 4, defined by Wolf. And next, please. And there you take you can see a shot I took to look into that continuous shadow. Not that you can see much, but just to tell you it's there. But there is a lot of reflected light, and that's another issue when you start to work in the details. Next, please. Now, what I did was take pairs. First, I was interested in the Alpha+Beta component, particle component of the Is-FeO per million year per part per million uranium plus thorium. And the shaded sample, which is in that continuously shadowed area, 76240, compared with a buried sample of both of different concentrations of uranium thorium, using them together, it gives you a delta between those two samples of Is-FeO of 11. And again, buried, shaded and buried simultaneously at 19.5 million years. Well, you can see an equation there. You put that all together, and you can actually calculate the delta Is-FeO per million year per part per million uranium as being 0.58. And and you can do that because of the different uranium plus thorium contents of the two samples. So you have with this, if you get a uranium plus thorium measurement, you have a rate at which those particular samples matured. Next slide. Now, what about solar protons, which we've been talking about quite a bit this afternoon? There is another pair of samples that can give you the similar analysis, and that is the 76220, which was taken in the last crater formed by the boulder before it came to rest. And that's been exposed continuously over time. So it has a very strong exposure to proton radiation from obviously from the solar wind. Now you take that with that shaded sample we already talked about, the 76240, and the difference there in delta Is-FeO is 10. And you can run through another set of equations because of that difference, and also taking into account the difference in uranium-thorium concentrations, and you can come up with a delta Is-FeO per million years of 11, approximately the same. Remember, the other one is per part per million uranium plus thorium, and so you have to know the amount of uranium plus thorium in samples to use this. Now, there's a nuance, an important nuance, to the proton data. The deep drill core nitrogen isotope fractionation data indicate that the energy of the solar wind increased by a factor of 3.4 about 100 million years ago. And I've talked to solar physicists, and it's not in their models or anything like that, but I can show you the data. Next slide. So when you introduce that 3.4 million years, then it lowers the rate of maturation by protons earlier in lunar history, prior to 100 million years ago. This is Clayton and et al. Data on the nitrogen isotope fractionation of the various zones within the deep drill core. And you can see, just look at the black lines and the black zone letters, and you see that they are coming from a very low del 15 nitrogen and if you take that down to 0, it turns out that in the early history of the moon, that ratio at accretion probably was about plus 80, if I remember 84, if I remember the number right. So by extending that trend, you actually can look back into lunar history. However, at about 400 million years ago, something changed, and that's the green. All of a sudden, your ratios start to get towards a much less negative del 15 nitrogen. And actually, here and with some other more detailed analysis, it looks like that del 15 nitrogen not only became stable, but is what we have today at about a minus 118. That doesn't jibe, by the way. Those of you that may know about the is it the Genesis spacecraft that crashed? Do I have that name right? Yeah, they came up with a minus with a minus 405, I think, from the analysis of the wreckage of that spacecraft. So there's a big discrepancy here between what that said and what this tends to indicate. But at about 100 million years ago, that change occurred, and the red points here show not only the trend of two of the top two zones, the youngest zones in the deep drill core, but also all other surface samples are on a totally different trend. And so that is what I'm saying is a trend that is 3.4, a factor of 3.4 more energetic solar wind in the last 100 million years than existed before that. Now we take this data, next, please. Next. And you can apply it to the light mantle deposits. And there you see 27 to 32 million years age on the young light mantle, on the old light mantle, slightly older. And there has to be an ancient light mantle as well. And I think we really do have imagery of all three. I'm not absolutely positive about the ancient light mantle there, but you see, this turns out to be a lot younger than I originally suspected from a different type of analysis. That's one of the problems of doing synthesis, is that you all of a sudden learn something and you have to go back. You get into a cul-de-sac and you have to get out of it, and it takes quite a bit of while. You have to revise your whole picture. But this, I think, now is getting very close because of the ability of those pairs of samples to give us the rates of exposure age. Next, please. I think this is the last one. And this is just to tell you, tickle you a little bit, is that when you apply all of that to every zone, you actually come up not only with the exposure ages of the zone, but when you total those exposure ages, you get the total age represented by the core, and it's just slightly under, with some significant error margin, probably slightly under 1 billion years. I was skeptical of Wasserberg early suggestion that the core represented about 1 billion years from the neutron probe, but I think he was probably right. Thank you.